Okay, so let's chit chat about the assignment from yesterday. Let's do that. So, because if your answer to 34A is wrong, about everything else is going to be wrong. So, bless you.
Thank you.
So on that one, you're going to find like that value of, what do they want you to find? Okay, you're just writing the expression on 34A. So on your B, that time should be like a really small number. And then on C, let me see the paper.
This one?
Yeah.
Okay.
Now, here's what you have to be careful of on 34C. So you want the calculation, you want the concentration to be after 5 times 10 to the minus 3rd seconds has elapsed. Now, here's what you have to look at. So this is some generic of A decomposing into B plus C. Maybe it's hydrogen peroxide decomposing into water and oxygen, okay? Magnesium oxide decomposing into magnesium and oxygen. It doesn't make any difference. It's a binary thing, and it's just going to decompose, all right? So here's the deal. Here, when you do the calculation, because you're told that it is a rate's constant, integrated rate law, all this good stuff. So, and it's zero order. So what this means is that when you look at A turning into B, you're told that the initial concentration of A was 1.0 times 10 to the minus 3rd, okay? These are both going to start off at 0. Now, what you find, and this is going to be important, what you find when you plug in that A equals -5 times 10 to the minus 2nd molarity per second times time plus A naught, okay? What you're finding when you do this calculation, this is what you have to think through. What you're finding at that point, what you're going to get out of this, okay, is 7.5 times 10 to the negative 4th, okay? That's the concentration of A at that point, okay? That's the concentration of A. It's not the concentration of B. So this is what you have to think through the stoich on this thing. So this is this initial set of conditions. Here's your change. Here's where we are at this point. So at this point, the concentration of A is 7.5 times 10 to the negative 4th. Okay, so this is where this gets tricky, because all of this is in a 1-to-1 ratio. Whatever you lose here from A is what you pick up at B. So this is the tricky part of this problem, is that you have to figure out what you have to subtract from this concentration to get this concentration that you're actually going to end up as the concentration of B, which oddly enough would also be the concentration of C, because that's in a 1-to-1 ratio. Okay? So I'll tell you right now, your answer to C is not that 7.5 times 10 to the negative 4th. That is not your answer, because they're not asking for the concentration of A at that point. They're asking for the concentration of B. Okay, so that's why you have to look at the stoich. Here's my concern on these calculations, is that you all are phenomenal at plugging numbers into calculators. You're amazing at that, okay? You're top shelf. But you don't know what the numbers mean, okay? Because you're calculating, the oracle speaks to you and says, oh, the oracle says the answer is 7.5 times 10 to the negative 4th, and that's what I'm going to write down, okay? But that is the concentration of A at that point, but that's not what it's asking, okay? So that's what you want to think through on number 34. On the question with the where you're given the data on 53, so your graph should look something like this, where you have the natural log of K and you have 1 over temperature in Kelvin, and it should be kind of a linear function like that. Now, especially on this, there's a huge variance in terms of what you get for your answer, depending upon which points you pick for your slope, okay? So, and that's gonna change a whole bunch of things. So, your slope, roughly, should be something times 10 to the third, okay? Something around there, that should be your slope. Now, this whole thing comes off of the idea that the natural log of k equals negative e sub a over r times 1 over temperature in Kelvin plus the natural log of a. And this is an orientation factor. Don't worry about that, okay? Don't worry about it. It's just your y-intercept. Don't worry about it. What you're searching for, and this is what's going to happen in the lab, is that you're searching for the activation energy. So you set that slope equal to negative e sub a over r. Make sure you're using 8.314 joules per mole Kelvin. Multiply that by the slope. Your kelvins will cancel out. You get activation energy. Okay, and activation energy is, you can think of it in terms of like how high the bar is that you have to jump over to start the reaction. Okay, so your activation energy, and again, there's some variance in this depending upon your slope, but your overall activation energy should be something times 10 to the 4th joules per mole. If you're into kilojoules, it's around 10 to 15. Okay? But again, there, depending upon which points you pick on that slope, there's going to be some variation. So the only thing I can really judge is the work that you have. On number 39, let me see your paper for a second.
Sorry.
That's good. So on 39, where the first thing that you have to calculate is a rate constant, because if that's wrong, everything is going to be wrong. So on 39A, that should start with a 1 and then be something times 10 to the minus third. Because if that's wrong, everything's just going to be a train wreck. And your half-life on 39 should be around 700 seconds.
Can we go over 25B?
Yep.
Would you say the half-life should be around
On which one?
for 39?
Around 700.
Okay.
That was the gases?
Yeah, and it had like torque or something like that.
Yeah. And what do they give you?
I'm not sure.
Okay.
It's 56 to a minute.
Yeah.
And for the decrease.
Moles per. And then, okay, so let's talk about, make sure everybody's cool with 25A, because 25, we don't have 25A wrong, but 25B is also going to be trained wrong. So on this one, they're told you that hydrogen is being consumed at 0.48 moles per second. So that's actually pretty fast, because if you consider, just to kind of put this in perspective, anybody remember if you have a mole of hydrogen gas, how many liters that is?
22.4.
22.4, which is about enough to fill up that water jug. Okay, that's about 22.4 liters. So if you have a half a mole, that's about a volume of about half of that jug. So what we're saying here is that when you, this is why this reaction takes place so quickly, like when we light the hydrogen balloon, okay? it happens really, really quickly because you're going to consume that water, about half that water jug full of hydrogen per second. Okay? So that's why when you light that, bam, that goes really, really quickly. So, and that one you can do the stoic, you can set it up as like, if you like the fractions, or you can go like 1/2 and then 1/1 and or whatever those, doesn't make you, I don't care how you get to that point. Now, on B, you're given this other reaction of 2NO plus Cl2 yields 2 NaCl. It's highly pressurized. Okay. So, okay, so here's the deal. So when you have, and we haven't really got to gas laws, torr is just a measure of pressure. If there's ever a quantity in science that has an identity crisis, it's pressure. Because it can be measured in a whole bunch of different things. It can be measured in torr, it can be measured in inches of mercury, millimeters of mercury, pascals, kilopascals, psi, kilogram per square inch, or per square centimeter. I mean, there's a huge variety of ways that you can measure this. Okay, so in this case, it happens to be measured in torr. 760 torr is equal to like 1 atmospheric pressure, which is about what we're at. So basically, if you think about what's happening inside this reaction vessel, okay? So you kind of got to visualize what's creating pressure, okay? Pressure is created by these little particles, right, of nitrogen and oxygen bouncing around, and you got some chlorine gas in there as well. So this pressure is created by all these little particles hitting the sides of the container. So as the reaction progresses, you're going to decrease the number of NO particles, and you're going to decrease the number of oxygen particles. But you're going to increase the number of NaCl particles that are being created. So for every like one reaction, you're losing 3 particles, okay, because that's what's going to get consumed, but then you're gaining 2 over there. So your overall net change as this reaction proceeds is actually overall decreasing the number of particles within the system, okay? Because 2 are combining in, or 3 are combining into 2. So the overall number of particles in the system is going to drop because it's a synthesis reaction. So when you look at this, so you're told that the NO2 is decreasing at 56 torr per minute. So then you can also then figure out the rate at which your Cl2 is decreasing. So if you like stoic, okay, you can sit here and go, well, that's 56 torr per minute, and that's my nitrogen monoxide. So if you do a little bit of stoic, you can sit here and go, okay, well, I got 2 moles of NO to every 1 mole of chlorine, right? So then what's the rate at which my Cl2 is being consumed? Twice as much or half of 56? Half of 56. So my NO, because that's being consumed at 56, my Cl2 is going to be consumed at 28. Okay? So I got one dropping at 56 torr per minute. I got another one dropping at 28 torr per minute. Okay? Well, what's happening? Okay, we're combining these things. Now, on the other side of it, what am I doing in terms of making NaCl? I'm making NaCl, right? Mm-hmm. So, because of the fact that you know that same stoic, okay, so if you've got 56 torr per minute of your, NO, I can also figure out the rate at which my, because that's a 1-to-1 ratio. So for, because this is 2-to-2, but it's a 1-to-1 ratio, right? So if I'm losing 56 torr of NO, guess what? I'm gaining 56 torr of NOCO, okay, because it's just a simple story. Now, what it's asking for, what are the rates of change of, what is the rate of change in the total pressure of the vessel? So think this through for just a second, right? So you've got, which one is this? 25. So here's the deal. So you're losing 56 on your NOCO, okay? Of your NO, you're losing 56 there. You're losing another 28 in terms of your CL2. But I'm gaining 56 over there. So what's the total pressure that I'm losing per minute?
28.
That I'm losing, right? Because I'm losing 56 and I'm losing,
90, 20.
so those two are decreasing, right? But I'm gaining 56. So what's my overall net change? Negative 28. So what's going to happen is that over a period of time then, what you would see is that the pressure inside that container is decreasing. So if you go with like the Timmy analogy, okay, you've got like two Timmys and a Susie. So you've got these three kids bouncing around inside your classroom. They're going to combine into two. So you're going to go from 3 to 2. So over a period of time, I'm going to decrease the number of kids that are bouncing around inside the classroom. As I decrease the number of kids that are bouncing around inside the classroom, what's going to happen to the overall pressure? It's going to go down. Now, if you reverse this, what would happen to the pressure? Then it would increase because you'd have 2 forming 3. Okay?
Yep.
Does that make sense?
Yeah.
Okay.
The book didn't
Fantastic.
explain it very well.
Huh?
The book didn't explain it very well.
Well, that's why I'm here. To try and explain it a little bit better.
Thanks, man.
That's all. Okay. Anything else you want me to go over? At all? Going once? Going twice? So,
Question, what did you get for 34C?
yeah, stop that. All right, so there's a couple of things that are going to play into this lecture that we kind of have to, that they're going to seem random, but eventually they're going to get all merged together. So here's the first thing that we have to get straight, is that you all are used to reactions taking place like in one step, okay? It's called an elementary reaction. You all are used to saying, oh, hydrogen combines with oxygen and we get water. Boom, there you go. That's it, one step. But the problem is that a lot of times when you get into more complex reactions, like the lab that you're going to do on Monday with acetone and iodine and hydrochloric acid, that's a very, very complex reaction that involves actually some hidden steps. We write it as one reaction, but in reality, we know that there's some other things that are happening. So when you deal with rate determining steps, number one, this is only going to be important when you have reactions that occur in stages, okay? So hydrogen and oxygen combining when we light the balloon, we don't have to worry about that because that's only going to happen in one step. Lab that you can do on Monday where you have some things happening beyond, like kind of like the Wizard of Oz, like behind the scenes. So we've got to try and pull back the curtain and figure out, okay, what's actually causing the reaction to take place. So here's your overall guiding rule, okay? Is that no reaction can take place faster than the slowest step in the multi-step process. So here's kind of a visual way that you can do this. So imagine that you have 3 funnels, okay? So you kind of got a medium-sized funnel, and then that's going to pour into like a really small funnel, okay? And then that's going to pour into like this big, massive funnel, okay? And you're going to begin to pour water into the medium-sized funnel, okay? So what's going to determine the amount of water that we can get out of the bottom?
That middle funnel.
the middle one, right? Because you can pour a whole bunch of water into here. But eventually, when you do that, what's going to happen to that funnel? What's it going to do?
Overflow.
Yeah, it's going to overflow. At least it's going to get full, right? So I can't put more water into here than I can get out of here. Now, once it hits here, it doesn't matter. Okay, it's this big, massive funnel. Cool. Doesn't matter. So this reaction can take place relatively quickly. This is what's going to slow us down. So I can't get more water out of here than what I start with, what I can get out of this. Now, here's the other thing that's going to happen in terms of equilibrium, and this is where we're going to tie equilibrium into this thing. If this is a reaction, basically what's going to happen is that we will reach a point of equilibrium, where the water coming into here is going to equal the water coming out. Okay? Because that's what's going to establish this equilibrium. I could dump a whole bunch of water into here to start with, but eventually this is what's going to slow us down, and I can reach a point of equilibrium. So here's your rule. Okay? Your reaction can't take place faster than the slowest step. Okay? That determines your rate. Now, keep that in mind. So on the lecture notes that I gave you, okay, this is kind of just like a summary of a bunch of terminology and some things, so you don't have to like write stuff down. But if you look on these lecture notes, so I'm going to kind of go through this. This really kind of makes sense just when you begin to look at some steps and some actual reactions. That's slow and that's fast. Okay. So in terms of terminology, when you have a multi-step process, a lot of times you create what's known as an intermediary. An intermediate appears and you make it, but then it gets consumed later on. Okay? So it's all, and to a certain degree, this is like what you all did when you were balancing half reactions, and you had like one thing, like you had 6 water molecules on the other, and you had 4 water molecules on the other, and you could like cancel those out. We're going to do the same thing here, okay? So it's that same idea. So what's happening here is that this is my slow step. So nitrogen dioxide can combine to produce nitrogen trioxide and nitrogen monoxide. So out of this step, I'm going to make some NO3. But then that NO3 is going to get consumed down here. So I'm going to make it, but because this is the fast step, as soon as this gets made here, it's going to get consumed in the next step. So even though this is my slow step, I'm going to make some NO3, but then I'm going to consume it as soon as I can. But this is going to be my slow step. So what that means is that my slow step, I know, is kind of going to be based upon the concentration of these NO2 molecules. So the NO3 is what we call an intermediate step. So this is kind of a cool way to visualize this. So if I take this, I toss this up in the air, right, it's purple, but it'll come back down as blue. Comes back down as purple. So imagine that you could take a picture of this thing up there at the top, okay? So up there at the top, it's kind of going through this transition. So I'm making this image like this, where it's separated, but then it gets consumed on the way back down. So that's somewhat a visual way to represent intermediate steps. I make it, but come on, turn color. There it goes. Comes back down as purple. So we make one thing there, we consume it very quickly. All right. Now, if you were to add these together, okay, what you'll see is that your nitrates cancel out, okay, those go away. I've got an NO2 that's going to cancel out, and I would add those together and I would get NO2 plus CO yielding NO plus CO2. So at the end of the day, when you add these reactions together, you're going to see almost all the time, it's rare that your intermediaries don't cancel out, Most of the time, that's the whole point, is that you produce them and then you consume them. So this would be my overall reaction. So this is a situation where if you were to look at just this reaction, okay, this would be based upon the concentration of my NO2 and my CO. So in other words, if this was an elementary reaction, it would only be dependent upon the concentration of my carbon monoxide and the concentration of my nitrogen dioxide. But what would happen is that when we actually looked at the reaction rate itself, we would notice that like it might be 0 order with respect to CO, but it might be like a second order with respect to my NO2. So even though this is what we know happens, we would have to come up with a series of mechanisms to explain why. Wow, why is it dependent upon just the concentration of NO2 and not the concentration of my CO? So we'd explain this in terms of having a mechanism that says, wow, if we make this happen, we can produce some NO3, it gets consumed, now we can make sense. Okay, so that's what happens when you've got to figure out like what's happening with the wizard, and you kind of got to pull the curtain back and say, okay, this is really simple, but it's like that's old adage that still waters run deep. Okay, it might appear simple, but obviously there is something much, much more complex that's happening behind the scenes. So that's kind of the whole point. So on this with the terminology, unimolecular, bimolecular, termolecular, that's just how many things have to collide to make something happen. Now, when you get to bimolecular, that's the one that happens most often. Unimolecular is generally just, hey, one thing decomposes. It's just a decomposition reaction. Bimolecular is the one that you will see most often. Now, with bimolecular, I want you to get one thing straight. It doesn't necessarily mean that it's two different types of molecules, okay? It could be like oxygen, for example, forming to form ozone. So even though that's just oxygen, that's still considered a bimolecular reaction because you have two oxygen molecules that are going to collide. So now that would also be, bimolecular would also be if you had like hydrogen and oxygen combining to produce water. That would also be bimolecular because it's hydrogen and oxygen. Oh, now, termolecular, meaning like 3 or more, generally 3, that's rare. Mainly because statistically for that to happen, you can kind of visualize it as being like a lock and key. So if you have one lock and one key, that would be like a bimolecular. Okay, in other words, imagine that we set like a 5-gallon container. And we throw in a bunch of locks and we throw in a bunch of keys and we just begin to shake it up, right? And we're going to have these random collisions. Well, a reaction is going to occur if in that random collision the lock happens to slide, the key happens to slide inside the lock. Okay, that would be considered a win. Okay, that would be a reaction. So if you now consider that having one lock, but you've got to have 2 keys that have to collide just right to make it happen. If that's the case, that reaction is going to be much, much less likely to happen. Because now you'd have to have 2 keys hitting at just the right angle with just the right lock. Again, it could happen, but not so much. Now, this is also where temperature plays into it. Because if you consider this idea of like random collisions, well, at higher temperatures, you're going to have more collisions. As more collisions happen, you're going to be more likely to have that lock combined with that key. So this is why as temperature goes up, your reaction rates goes up because of the fact that you're going to have more random collisions that will make that reaction take place. Okay, so let me kind of work through what's going to happen down on this example. Now, there's a couple of things that are important about, this is just the one that you all have on here, okay? So let me explain some subtleties about this reaction. Notice that this reaction here has this double arrow. So what that means is that this reaction has the capacity to reach an equilibrium point where the forward rate of the reaction can equal the reverse rate of the reaction. So that would be like, remember what we did that very first day, and we had the tubs of water, and the man was pouring into one and I was pouring back into the other, and we eventually reached that point of equilibrium, okay? That's what could happen here. But here's my slow step, okay, right? And then basically what's going to happen is that as fast as I produce Y, then it gets consumed down there. So, Noah Hale, what are my intermediaries in this reaction?
Trying to read here.
Well, it's the same thing that's on your paper, on your lecture notes.
Like the steps with the bees, right?
Huh?
The steps with the bees that you're talking about?
Let me ask you this differently. Tell me something that is produced and then consumed in the reaction.
So what's the overall reaction?
No, that's not right. We'll get to that.
Okay.
We'll get to
The
that.
X's.
Okay, X, because I'm going to produce X here, and then guess what? I'm going to consume it there, right? Okay. Then what's the other one?
Would it be B?
Why?
Y?
Because I produce it here and I consume it here.
Oh, I didn't see that plus Y.
That's why I said.
I was like, where's the Y coming from? I was
Yeah,
very confused.
that Y. Okay? Now, overall, what's my reaction?
A plus B.
Well, 2A plus
2B
2B,
yields C and D.
C plus D, right? That's my overall reaction. So, what would happen here physically is that you're going to rapidly produce X. Then you're going to create a traffic jam. X is going to start to get backed up. If you produce enough X here, then what will happen is that it will start to decompose back into making A and A. So if we produce so much of this, it's a traffic jam. This reaction gets reversed, and now we establish a new equilibrium. So this would be like Amanda dumping a whole bunch of water into my container at first, but then eventually her container is going to drop so much that now I can start to put back water into hers at the same rate that she's going to put water into mine. So initially we would produce a bunch of X, but then it's going to slow down and form this. But if I back up X enough, I start to establish new equilibrium where this goes, yeah, I'm making A and A to make X, but X is also decomposing back into A and A. Okay? Kind of got the idea of how your intermediaries work. Okay. Now, let me kind of go through one big thing and then we'll call it good. So, here's what we've got so far, right? So, since this is my slow step right here, okay, that's my slow step. If that's the only thing that's happening, then the rate of this reaction would be written as K times X plus, oh, I screwed that up. Hold on, not X plus. Okay? So, if this was a single elementary step reaction, I would just say the rate, since this is my slow step, it would only be dependent upon the concentration of X and the concentration of B. Okay? If it was a single step mechanism, these would, because that's my slowest step, That's what it would depend on, nothing else. Now, here's the problem. I can't have X in here because X is an intermediary. So I've got to rewrite this somehow or I can get rid of X. Okay, I need to make X go away. But here's the whole key to this. Because of the fact that this is going to reach an equilibrium up here, okay? Now, once it reaches equilibrium, what do you think is going to happen to the rate of the forward reaction and the rate of the reverse reaction?
The rate of the reverse reaction is going to increase.
No. Once it reaches equilibrium,
Oh, it's going to balance out.
it's going to balance out. The two rates are going to be equal. The rate at which Amanda poured water into me is the rate at which I would dump water back to Amanda's. Okay? Reaction's still happening, but that water level, the exchange of water is going to be the same. Okay? So, I'm going to rewrite this. Now, I'm just going to put a generic K. I don't know what the rate constant is. I don't care what the rate constant is. I honestly don't care. It's not the point of the story. But what I can say is, because that's going to reach a point of equilibrium, then the rate forward, which I would write as, I'm just going to call it K forward, which is A times A, is going to equal the K in the reverse, and the K in the reverse is only dependent upon the concentration of X, not A. Got a little happy writing my A's. And that's going to equal the rate of my reverse. Now, if I solve this for X, okay? If I solve this for X, that's just going to be divide by KR. So now, these are just two K values. Again, I don't know what the K values are. Doesn't matter. Okay? I don't care. We'll figure that out later. All I know is that this is just going to give me another K value. That's it. It's just going to give me another K value. So I can write this as some K times A times A, which is going to be my concentration of X. So now what I'm going to do is I'm going to take that and slam that into here. Okay? So now I've got R equals K times A squared B. So this is something that I can deal with, because once I get it to this point, now, oh, this is dependent upon my concentration of A and dependent upon my concentration of B. I've eliminated those intermediaries. I don't have my X, I don't have Y. Now, physically, this becomes tough to actually set up, and here's the reason why. When you look at, no pun intended here when I said Y, so if I produce Y out of this step, Y is immediately going to get consumed. So if you were to actually run this experiment, it would be incredibly difficult to actually detect the presence of Y, because as soon as I make it, it's going to get consumed over there. So sometimes you have mechanisms where you say, logically it makes sense that I'm going to make this, but it's going to be so fleeting that we won't actually be able to detect it. Now, like, we could detect the presence of X, because X is going to back up, and it's going to start to establish this equilibrium. So we could maybe X is an ion, okay, that has a particular color to it. Maybe it's a permanganate ion. Maybe it's a hydronium ion where we could shift a change in the pH. Maybe it's an ion that has like a particular color to it that we can run through a spec 20, which we'll do later, or just observe it. So I could certainly detect the presence of X, because this is going to establish an equilibrium. I could make Y out of this, but odds are I'd never actually be able to see it because it's going to get produced, you're going to make it, boom, it's going to get consumed. So it's kind of like, you're at a home football game, okay, and it's really, really cold outside, and everybody's outside, and the concession stand is making hot chocolate, right? Well, as soon as it makes hot chocolate, boom, it gets consumed. So you know people are making hot chocolate, but you can't detect the presence of it because as soon as you make the hot chocolate, it gets consumed, okay? Now, if they were making like, if they were selling, I don't know, cheese-covered broccoli, okay, I guarantee you that's going to be your slow step because not that many people are going to be eating cheese-covered broccoli at a home football game when it's cold outside. Then you got to be hardcore. Pearson might, okay, but he's about the only person I know that would. So, I'm just saying. So, when you look at that, you can detect the presence of the cheese-covered broccoli because that's going to reach that equilibrium point because that's going to be your slow step. Producing hot chocolate, boom, that's going to get consumed right away. Kind of see the difference between the two. Okay. All right, so here's this last actual example with real stuff, okay? And again, this is on your lecture notes, okay? Don't write this down. It's this one. I'm going to work through this bottom one here. Don't write it. It's already there. If you want to write it down, you can. So you got NO plus NO into O2 to Nobra, or to Nobra, I should say. Okay, so here's the deal. Start with this. What can you cancel out? Party girl, what's my intermediate? Into O2, right? Okay. I have arrows there, so that means I can reach a point of equilibrium, right? Okay, that's cool. So what I end up overall is 2NO plus Br2 yielding 2 Nober. So into O2 is my intermediate. It's going to produce it. I'm going to make it really, really fast. I'm going to make a whole bunch of it. But this is going to create a backlog because this is my slow step. So eventually, this thing is going to start to decompose back into NO and NO. Okay? So visualize this. I'm going to make a whole bunch of this. This is like making the cheese-covered broccoli. I'm going to make a whole bunch of cheese-covered broccoli to start off with, but guess what? Not very many people are going to use it because that's my slow step. Okay? So eventually I'm going to be taking that broccoli and I'm going to be taking the cheese back off of it, and then I'm going to use cheese maybe to something people would eat. Like I'm going to put that cheese on nachos or something. Okay? But I'm going to make this. Eventually I will be able to detect this presence because I'm going to make a lot of it. So here's the deal. So when I look at this being my slow step, if this was a one-step mechanism, I would say, oh, okay, that rate then is going to be my sum K times into O2 times the concentration of Br2. But I can't have this in my overall reaction rate. Why? Because it's an intermediate. I'm going to produce it, I'm going to consume it, so I can't have this. But because this reaches a point of equilibrium, okay, that reaches a point of equilibrium, so I'm going to take this one and I'm going to roll this into, oh, here's the rate of my forward, which is going to be my concentration of my NOs, and there's a K in there, and that's going to equal that reverse reaction, which is going to be sum K times my into O2, okay? So, here's the deal. Now I can sit here and go, oh, instead of into O2, guess what? I can take this and substitute that in for here. So then I can rewrite it as R equals sum K times my NO2, or my NO, I got too many O's floating around. Now, here's what we're ultimately after. In terms of what we observe. So, what this mechanism allows us to happen is so this is my overall rate now. So, it's second order with respect to NO. It's first order with respect to BR2. Okay? And then I can figure out what that K value is. So if this was my rate, if I doubled my concentration of my NO, what would happen to my rate? It'd go up by a factor of 4. If I doubled my BR2, my rate would also double. Okay? So what this is allowing us to do is to explain why this is dependent upon those concentrations. Got it? It's really not that tough kind of once you kind of see and get used to the terminology.
Sure.
All right, stop that camera. Okay, so let me explain what's going to happen on this, because this is kind of a summary of a lot of the things that we've done so far. So this one, I've given you 3 different experiments: concentration of A, concentration of B, initial rate of formation of D. You determine the rate law for the reaction. So this is the process where you've got to choose ones to cancel out, okay? And you can say, oh, okay, well, I want to isolate A or I want to isolate B, okay? So your rate law, when you get done with that, this isn't the integrated rate law, it's just the rate law. So you're going to have R equals K times whatever you think that is, okay? Then you're going to calculate the rate constant K, right? Now, when you get down to number 3, I've given you 2 different scenarios as far as mechanisms for this reaction. Scenario number 1, A plus B forms C plus E, that's a slow step. And then you're going to take A plus E, that's going to be your fast step. Over there, list your intermediates. Then the same thing. Now, here's the deal. Remember, your slow step determines the rate. So what you want to do is look at these 2 possible mechanisms and pick out which one matches your rate that you found up on number 1. Okay? So you can't do that one until you figure out what that rate's going to be. On number 4, this is you're producing this complex ion. Complex ions are cool because they typically have like a really cool color to them. So I've given you a half-life of 14.5 degrees. Under these conditions, how long would it take to decrease to 12.5%? And I tell you, it's first order, okay? It's first order, right? On the back sides, these are elementary steps. Do not make this simple or do not make this complicated, because these are elementary reactions. There's no hidden thing. There's no wizard behind the scenes. Your rate is just going to be determined by the concentration of your reactants, okay? Then on 7, you're back to, oh, here's a series of steps. Then you've got some questions from the textbook. So, I'm done. You're on your own. Mr. Carter, shut down that camera, please.